Okay, we're going to be moving on to chapter 21. So that this is the carboxylic acid derivatives. So in here we're talking about not only regular carboxylic acids, but also acid halides, anhydrides, esters, amides, thioesters, acid phosphates. We're not going to be doing a whole lot with acid phosphates, but the other ones we're going to be doing, talking about reactions and how to name them and whatnot. Like that. So naming carboxylic acid derivatives, there's a whole bunch of these, and they all have their own little quirks. A lot of this is having to do with historical reasons. A lot of these things were characterized and synthesized before they knew what the actual structures were, stuff like that. And so it was sort of a hodgepodge of names, stuff like that. So keeping them straight is going to be a little difficult, but hopefully it won't be too bad. Stuff like that. So start off, we're talking about acid halides, stuff like that. So with these are where you have a C double bond O with either, it's usually typically either chlorine or a bromine hanging off of them, stuff like that. And so again, you have to find the do the 4 steps. Find and name the parent chain containing that acid halide, right? So it'd be very similar to naming like an aldehyde. It's going to be the end of the chain, stuff like that. And so you have to have that the acid chloride functional group within there, stuff like that. And so at the end, after you find the longest chain, you take off the E off the name of the regular chain, and add oil, OYL, and then whatever the halide is. So if there's chlorine there, it would be like pentanoyl chloride. If there was a bromine, it would be pentanoyl bromide. If it was acid fluoride, it would be a pentanoyl fluoride. Stuff like that. So and on and on and on. Stuff like that. So, again, you name the side chains, right? Stuff like that. So remember that chloride is part of the acid chloride group, so you don't have to name that, or the acid halide, and that. Do the side chains, right? So acid halide, just like aldehydes, the carbon with the acid halide group is going to be carbon 1. So you just go out from there, and then put the side chains in alphabetical order with their position names, and then put the parent chain at the end. So like that. So here we go. So Cl and then this fluoride here. Okay, so here's your right. So you can always put in the dots, right? Right. So 1, 2. Right. Here's the only carbons, right? 1, 2, 3, 4, 5, 6. Right. So BC6. So that would be hexane. Right. We're going to take off that E and make it hexanoyl chloride because it's a acid chloride, right? Because there's that chloride there. Okay. So that's your main chain. Okay. So about that, and so, right. So that's your main chain there, right? So then we've got this, the fluorine here. So fluorine or fluoro, right? So the numbering is 1, 2, 3, 4, 5, 6, right? So where that acid chloride is, that's going to be carbon 1. Right? So this is hanging off of 4, so it becomes 4-fluoro hexanoyl chloride. Okay, you don't have to name this one. That's part of the acid chloride functional group, right? But you do have to do that one. How about that? Okay. Next up, anhydrides. Okay, so remember, anhydrides are going to have this functionality to them too. You're going to have 2 C double bond O's with an oxygen in between it. Okay, so like that. And so you have to figure out is the left side the same as the right side? If there is, then it becomes easy, right? So you're gonna take a look at this side and that side. If these two are the same, then all you have to do is really name one of them, because in this case it's assumed that the other one is going to be the same one, stuff like that, and then put anhydride at the end. So again, you just do one side. Okay, so find a name parent chain of the carboxylic acid, right? So of the C double bond O, so you go out this way, you just pick one of them, and then at the end it would be oic anhydride, stuff like that. So at the end of the name, right? So do side chains. The C double bond O here is going to be carbon 1, so it'd be, if you're going to do the right side here, it'd be 1, 2, 3, 4, going on out, stuff like that, and then similar name as normal, but the parent chain at the end. Okay, and so if you have something like this, that. Okay, put in your dots for your carbons if you want. Okay, so you take a look at that side and this side. right? So with that, so you have the blue side and the black side, right, left and right. Notice how they're mirror images of each other. So that means that you only have to name one side. Okay, and so the main chain is going to be 1, 2, 3, 4, or 1, 2, 3, 4. It doesn't really matter, so we'll take that as being the main chain, right? So C4, right? So it'd be butane, right? So it'd be butanoic anhydride. Okay, and then you have this methyl side chain here, so you have a methyl. Okay, and the numbering this is going to be carbon 1, right, where that C double bond O is. So 1, 2, 3, 4. Right. So it's going to be methyl at 3. So in this case, it's going to be 3-methyl butanoic anhydride. And it assumes that since you're only really naming one side, that means that they're both sides are symmetrical. Okay. Now for asymmetrical ones, it works very similarly to it, but you're going to have to name both sides. Okay. And then at the end, you're just going to need oic on the name of the parent chains, and then you're just going to throw anhydride at the end. But you bolt in the names of each side as needed, and you put the parent chain that's first alphabetically first. Okay, so about that. So here you have okay, so so you take a look at that side, and then you take a look at this side, and obviously they are different. Okay, so we're gonna have to name both sides independently. Okay, oop, got a carbon here. So okay, so here we go. All right, so this is going to be very similar to that, right? So you're going to have this is going to be C4, which butane, which normally be butane, but now it's butanoic, right? So with that, so right, so but then we have this methyl group, right? And carbon 1, 2, 3, 4, right? So this side becomes 3-methyl butanoic. Okay. So notice I put this in parentheses, and it'll be a little bit easier to show you what's going on in a minute. Why I put those in there. Now this side here, right? So you have the benzene ring, which normally the side chain would be phenyl, but it's a benzene with one carbon hanging off of it here, and so this ends up being benzoic. Benzoic. Okay. So with that, because this would be, if there was an H here, this would be benzoic acid. Okay. So with that, so this side ends up just being benzoic. If there were things hanging off of here, it would be, if there's a methyl group here, it would be 1, 2, 3 methyl benzoic, or whatever. Okay, so with that, but I'm going to put that in parentheses as well. Okay. Now you have to take a look at the parent chain, right? So here it'd be butanoic, here it'd be benzoic. Right, so benzoic is first alphabetically, so that gets listed first. So you just bolt these in as needed. So benzoic, 3-methyl butanoic, and then put anhydride at the end. Okay. Don't go about rearranging these methyl groups, like putting that out front or anything else like that. You just bolt it in, bolt that in first, and then bolt that in first, and then put anhydride at the end. That's all you got to do. Don't overthink it. So, okay, esters. Okay, so the naming of esters is a little odd, and again, it has to deal with the issue of how they were originally synthesized. So usually, what they would do is they would take a carboxylic acid and then add an alcohol and put a little bit of acid in there, and they would react. It would be Fischer esterification, and then basically they would combine together and squirt out water, which that reaction we'll talk about in a minute. Something like that. But the way that they named it was the alcohol that they put in originally, and then they put in the carboxylic acid name after that. Okay, so Oop. Come on. But the so what you end up having to do is, so you have this is a classic ester, right? So with that, so what you're going to do is you're going to name, this is the C double bond O side, and then you're going to name the oxygen side, right? But what ends up happening is the name always ends up being, you name the O side, okay, of this ester bond, but you name this as a side chain, okay? So like that, and then after that you end up, so the final name ends up being the C double bond O side plus the C double bond, or the O side, and then the C double bond O side, okay? It doesn't matter if it just bolts in just like the other one, okay? So like that. So this side here is going to be, the C double bond O is going to be your main chain, okay? And you're going to replace it with O8, the ending with the suffix with O8, or sometimes it's just 8. Usually it's O8, right? So like that. So here we go. So a very simple ester here. Okay. So we have the right. So we have the O side here, right? So we have a 2-carbon piece. So the O side, right? So it's 2 carbons, right? So that would normally be ethane, right? But since we're naming it as a side chain, it would be ethyl. Okay. That. Okay. And again, I put this in parentheses because we're just going to be bolting that in. Okay. Now the C double bond O side, right? So it's 1, 2, 3, 4, right? So it's C4, right? So it'd be that would be butane normally, but we're going to change that suffix to butanoate. Okay. And so what you end up doing is you end up putting this first and then that. Okay. So your final name becomes ethyl butanoate. Okay, so let's say if there was a methyl here, right, or fluoro or something like that, it would be ethyl, 3-fluorobutanoate. Okay, so with that, so with that, and so you just bolt these in. This goes in here, and then that goes last. Okay, so with that, so okay, so amides. Okay, amides. So that's, so what's going to end up happening is, now this is the nitrogen version of the ester, right? Okay, so you're going to have these groups hanging off of here. So your parent chain is going to start with the C double bond O and go away from it. Okay, you're not going to worry about the nitrogen next. Okay, now after you find the parent chain, right, you change the suffix, you take off the E and change the suffix to just amide. With that, so it's the easiest one to remember. So about that, but you're going to find and name all the side chains then. But these things, the groups hanging off the nitrogen, those are going to be considered just side chains. Okay, so if they're hanging off of the C double bond O side, right, you just name them with the normal numbers. If they're hanging off the nitrogen, you put, instead of a number, you put an N in front of it. Okay, and that just indicates it's hanging off that nitrogen. Okay, and then you put the side chains in order. It doesn't matter about the numbers of the ends or whatever. Just make sure you put them in front, but they go together alphabetically, and then put the parent chain at the end. Okay, and so if we have something like this, okay, you always put in your dots. Okay, so our main chain is going to be going away from the C double bond O, so it's 1, 2, 3, 4, right? So here it is, right? So with that, so this part here, C4, right? So it'd be butane. So it would become butanamide. Okay, now we have a methyl, right? An ethyl, and a propyl, because 1, 2, 3, 3 propyl, 3 carbons, so it's propyl. Okay, so this one here, this one is hanging off of carbon 1, 2, 3, 4. So this is hanging off of carbon 3, and then these guys are hanging off of carbon 1. Okay, so what comes first, right? Right. So the ethyl is going to come first, right? Because alphabetically, so it becomes N-ethyl. Methyl comes next, right? Because methyl comes before propyl, so 3 propyl. And then 3 methyl, sorry, I got ahead of myself, N propyl butanamide, right? We have a main chain that's 4 long, right? Oh, hey, it has an amide in it. right? Then you got three different functional groups, right? The propyl, right, and the ethyl are hanging off of that nitrogen of the amide. This methyl is hanging off of carbon 3 of the main chain. So there you go. Okay, so thioesters are going to be very similar in naming as regular esters, right? Because they're just the sulfur versions, right? So this is a thioester. Okay, so it's just the sulfur version of an ester. So we can name them the exact same way. So again, it's going to be the S plus this C double bond O. Okay, again, this is going to be named like a side chain. The S side is going to be named like a side chain. Okay, but this suffix here, right, if it was on the main chain, instead of O8, right, it says thioate, right, because thio typically means sulfur. Okay, so it's a sulfur ester. As you know, O8 would mean ester, thioate means sulfur ester, so thioate. Okay, so here we go. Chloride. Okay, so here we go. So we're going to do this side, right? So it's 2 carbons long, right? So the S side, right? So C2, right? So that would be ethane. Remember, we have to name it like a side chain, so it becomes ethyl. Okay, so then we have to do the C double bond O side, right? So this becomes 1, 2, 3, 4, 5, 6. So C6. So for the C double bond O, C6. So this becomes, it normally be hexane, right? We're going to take the E off and becomes hexane thioate. Okay, but remember we have this chlorine here, right? So we have a chloro. Okay, and this becomes, right, so 1, 2, 3, 4, 5, 6, right? So this, right, so it's hanging off of carbon 6. So it becomes 6 chloro hexane thioate. Okay, put these in parentheses, right? So again, it becomes this in front and then that, right? So the final name becomes ethyl 6 chloro hexane thioate. Okay, you know, you'd be tempted to say, oh, chloro comes before ethyl, so that should come here. But nope, that's not how it works. You just bolt this in, okay, and you bolt that in there. Okay, that's what, you know, the parentheses helps to remind you of that. You don't have to put those in, but it helps. Okay, so this is going to be named exactly like the ester. It's just you have the thioate. Okay, acyl phosphates, don't worry about them, right? Nobody names them, stuff like that. So okay, now in this picture, okay, you will notice that there's actually an issue with this. It's fine in chapter 7 book, but in the chapter 8 book, the amide is actually down here, but the ending name is here. The ester, it's actually here and then there. So they've swapped the ester and the amide. I don't know why they changed it. Going from 7 to 8, the graphic looks exactly the same. But other than that, except they switched it. Don't know what happened, but just be wary of that. Okay. So okay, now comes the fun part. I know the naming's there's a lot of different groups, so with a lot of really weird names, but you know, appreciate you staying awake. Stuff like that. And so this is actually, it seems to be a little bit easier to recognize from the chapter 19 stuff, which was the aldehydes and ketones and stuff like that. And so with an aldehyde, right, stuff like that. So right, you're gonna have a nucleophile, right? This comes in, you know, that goes there, and this gets pushed up. But the problem is when you get to this point, your nucleophile, if this double bond, or these lone pairs were collapsed back down to reform the C double bond O, what are you going to have to kick off? Well, you're going to have to break a carbon-hydrogen bond, which isn't going to happen. You break a carbon-carbon bond, which again isn't going to happen. Or you kick off your nucleophile, which just means you go back there. So it's stuck, and so you end up with you end up with the alcohol, right? You end up with the nucleophile, an OH plus the thing that attacked it, right? The nucleophile. But for acyl, right? So these carboxylic acid derivatives, so let's say it's an acid chloride, okay, when you get the nucleophile, again, you're going to get attack here, right, to form your what's called the tetrahedral intermediate. now this group is probably going to be fairly weak, and so this bond here is fairly weak. So when that collapses down, that's actually going to kick this away, and so what you're going to end up with is that C double bond O reforming, but now you've got your nucleophile plus your leaving group here. In this case, a chloride. Okay, so this is what's happening for nearly all the reactions that we're going to be discussing. Okay, so like that. So in order for us to do this, what ends up having to be is this group here, the stuff right next to the groups right next to the C double bond O have to be small, because we're getting nucleophilic attack. You got to get your nucleophile in there. So the smaller this is, the better, right? So so if you have a lot of groups here, right, it's going to be just pure sterics is going to keep this from reacting. Okay, if you only have, say this was just a methyl group here, there's almost no steric interactions here. So like that. So the smaller the group, the smaller this group here by the C double bond O, the faster the reaction. Okay. Now this list here, so acid chloride. Okay. Was it anhydride? Right, so thioester, ester, amide. Okay, now you're going to need to know this list. Okay, so with that, so usually it's acid chloride. It could be acid bromide and that sort of stuff too, but acid halide, whatever. But typically they're acid chlorides. Okay, so the way this works is the fact that with this list, you can go side to side, so you could go from one acid chloride to another. You can go to one thioester to another. That'd be fine. You can go down this list, so you can make an acid. You can take an acid chloride down to an anhydride. That's fine. You can take an anhydride down to a thioester. You can take an acid chloride down to an ester. No problem. But you cannot go back up. Okay, you can't take it. It's incredibly difficult. So we assume that there's no reaction from going from an ester to a thioester. If you have to do that, you have to go and do some other things. But just straight reaction like what we're doing, you can't go from an ester to a thioester. You can't go from an amide to an ester. It's really tough. You can go from one ester to another, right? You can go side to side, stuff like that. You can stay within this, and that's fine. But you can't go up. You can go down, you can go side to side, but you can't go up. So know this list. Okay. Okay, so a lot of these sort of general reactions, right, this is all it's going to be, okay? So for acid halides, right, they're at the very top, so you can make anhydrides, thioester, ester, or amide, just depending on what the groups you attack, whatever your nucleophile is that you're going to attack. Okay, so here, right, so if you have, say, an acid chloride, right, so then you have your nucleophile, right, this is going to attack here, kick up, collapse down, kick that chlorine away. And usually what typically happens is as this leaving group is going, it grabs a hydrogen along the way. And so you end up with this. Right? So by that, so and HCl. So one of these hydrogens ends up going with that chlorine to make HCl. Okay? And so notice you go from an H2 to an NH. One of these hydrogens have been snatched by whatever your leaving group is. But that's how all of these work. Right? So we're going from an acid chloride, right, to an amide. Right? We're going from acid chloride to an amide, so we're good. Okay? With that. So that's how all of these go. You're going to need to know this mechanism. Right? So we come in, attacks, kicks it up to form the tetrahedral intermediate. That collapses back down to reform the C double bond O. It kicks off your leaving group, but the leaving group comes back and rips off one of the hydrogens to form your amide, or whatever it is that you're looking for, and HCl in this case. Okay? You need to know this mechanism for the test. Okay, so here we go. So it's typically going to be the thing that has the double bonds, or has the lone pairs. That's going to be attacking. So that goes there, collapse up, down, kick away. So you're going to end up with, and then all this other stuff just kind of comes along for the ride. Okay. O, like that. So this 4 carbon piece is there, right? And as this thiol leaves, right, it's gonna snatch this hydrogen away. So you're gonna put the thiol. There you go. Next one, right? We go from a thioester to an ester. So we've gone down that list, so we're good. Right, so we went from thioester to ester, so we're good. Plus NH3, right? Okay, so this has a set of lone pairs on it, right? So you're going to go attack there, up, down, kick away. So you're going to end up with NH2, right? Because this thing is going to, this leaving group is going to snatch one of the hydrogens away. Oop, there's only one. There's only ethyl, right? So this H is from this group here, right? So it goes NH3, NH2, right? So, and you're going from an ester to an amide, so you're good. Okay. Okay, so for this one here, right, notice it's a, okay, you have a symmetrical anhydride. Now, for this type of reaction, if you have an anhydride, for a reaction, I'm only going to give you a symmetrical one, so it really does not matter which one you attack with. Okay, so here we go. So 1, 2, 3, 4. Right, so right here's where the lone pairs are. So that's going to attack. Don't worry about the fact that this is a big anhydrate group. It doesn't matter. Okay, it's going to react the same way as this one and this one. Right, this goes up, this goes down, and then kicks that away. So you're going to end up with 2, 3, 4, right, and then plus H O like that. Okay, just whatever this leaving group, right? It acts the same way as the alcohol. It's the same as the thiol, right? The carboxylic acid. We're good. Okay, but here's the issue, right? We're going from ester to thioester, right? That's going up the list. So that means this is no reaction. This is what, so this is actually wrong. Okay, this should be no reaction. Oh wait, no, we're going, I'm sorry. This is an ester, this is an anhydride. This is why it was right. So this does work. Sorry, that is it. It's been a long day. So, sorry, this does work. You're going from, I'm sorry, this is an anhydride to a thioester. That is fine. So, I knew that was right. So, we're good. Sorry about that. Okay, so the question becomes, how do we, if acid chlorides are at the top of the list, how do we make them, right? So, well, we have to, so what we end up having to do is we have to actually make them more energetic to the, to be able to make the thioester. And so what ends up happening is you end up taking, so let's say you have something like this, right? And you have compound called thionyl chloride. Now you don't need to know the mechanism, but what ends up happening is this ends up attacking here, up, down, kicking off a chlorine. That group becomes so reactive that the chlorine itself can come in and reattack up, down, and kick away the chloral sulfate, right? So to make the acid chloride. But its sole purpose in life is to change an OH into a Cl. Okay, it doesn't matter that it's attached to a acetyl bond O. All right, OH to Cl. Okay, stuff like that. So now, if you want to make an ester, right? So one of the ways that you can make an ester is to just do nucleophilic attack, right? So if you have a carboxylate, right, that's a good nucleophile. If you have a small, say, you have a good leaving group, something small, you can come in and do an attack. Flip that away and do a sterification. OCH3, right, plus I minus. Okay, that's a nice way of doing it. You can also do Fischer. This is what we were talking about before with Fischer esterification. Okay. So with that, so if you have right, so with that, and you say you want to put, let's say you want to swap this for a propyl group, right? you're going to end up needing doing H plus. Okay, you need to put a little bit of acid in here. But again, you end up having there, up, down, kick away. And so then your 3 carbon piece, right? Plus H and then OCH3, right? You going from ester to ester, right? That's fine. You're going side to side. You're good to go. Okay, but you can just swap the alcohol out of here. Okay. Now, if you want to know the mechanism, here it is. So it ends up being acid catalyst. So it ends up being that this ends up attacking here, and then your alcohol can attack and up and then collapse down and go over. It's really complicated. I'm not going to have you guys memorize that particular one. So about that, I'm going to have you do the other one, just the more general one. But if you want to work this out, that's actually kind of it's interesting. You have to. The problem is you're going to have to avoid the production of minus charges, right? Because as soon as you form a minus charge, it's going to gobble up all your acid catalyst, and so the reaction is going to stop. Stuff like that. So, or slow way down. Stuff like that. So, but essentially you're doing the same thing. You're just swapping basically alcohol groups from one ester to another. Okay? So there you go. Okay, so predict the product. Right? Okay, so here we go, right? So these lone pairs, right? They're up, down, kick away. Right? H. There you go. So, right, and you're going from ester to ester, so you're fine. Right? So with that, but it's just the normal stuff. Okay? I guess you want to ask catalyst in there. Okay? So if you have this guy, plus, right? Again, you're going to have that attack there, up. Doesn't matter if you attack there or down there. It's just whatever's more convenient for you. So with that, right? Right, so here's a 3 carbon piece, right? Coming off of here. And then as this thing leaves, it snatches one of those hydrogens, so. Right, and just as a double check, right, you're going from ester, so you're good. So, no problem. So there you go. Okay, now, one of the quirky things is if you're going to have if you have an acid, a carboxylic acid, right, and let's say a base, okay, and an amine, okay. So remember, nucleophiles are also bases, okay, and so if you just put these two reactants together, what's actually going to end up happening is this guy's actually going to attack there, push that over, and you're going to end up with the salt, the carboxylic acid salt, plus NH3 plus. Okay, so whenever you mix a carboxylic acid with it, which is a regular amine, it's just going to be a very simple acid-base reaction. Okay, so what you end up having to do, if you really want to couple these, okay, it is you have to throw in another compound called DCC. Okay, and what that does, okay, is it first reacts with your carboxylic acid, okay, and makes that into an ester. So now there's no reactive hydrogens there anymore, and so now this can do its normal attack. Okay, so you end up with your normal amide, right? Plus, oh yeah, that's it. So, okay, and then DCC ends up becoming DCU. So here's the mechanism of it. You don't need to know the mechanism, but essentially what it does is it converts this into a reactive ester, which then comes in and attacks. Okay, so so without the DCC, this reaction basically just becomes a carboxylic acid or acid-base reaction. With the DCC, you actually do get the coupling with that. So Okay. Now, one of the weirder things that's going to happen is you have to be very careful about if you're adding hydrogens or carbon groups to those to the carboxylic acid derivatives, because what ends up happening is let's say you have an acid chloride, something that's simple like that. So if you add lithium aluminum hydride, right, or borane, BH3, these are both going to be, let me write this in red, these are actually both going to be sources of hydride. Okay, and so what's going to happen is just normal stuff, up, down, kick away, and you're going to end up with this, your aldehyde. Okay, the problem is that is still incredibly reactive. Okay, and that these guys here have more than multiple hydrides, so what's going to end up happening is you're going to do a chapter 19 reaction where that's going to come up there and kick this away. It's going to be a normal aldehyde reaction, and so you're going to end up with your an OH plus two hydrogens hanging off of it. Okay, so when you're adding hydrogens, you're adding carbon groups, you're going to end up having two, because when you go through when you're adding hydrogens, you end up with this this aldehyde intermediate, right? So that's going to be the first step, but this is going to be too reactive, and so you're going to get another one in there, attack. Same thing happens with okay, so here we go. Predict the product. Oops, it's a poorly formed benzene. Okay, so you have this, OH, NH2, right? So in the presence of DCC, if not, then this isn't going to happen, right? That comes in, essentially it comes in, attacks, down, collapses, kicks away, and so you end up with NH, like that. Your cyclobutane, right, hanging off of here. Now with this guy, OH, okay, this should probably be more like well, anyway. So lithium aluminum hydride, okay, so remember this is a source of H minus, right, so that's going to attack there, up, down, kick away, and you're going to get this intermediate here, the aldehyde intermediate. Oh, forgot my methyls. Okay, and then another one is going to come in and attack there, up, down, just up. Okay, so you're going to end up with just the alcohol at the end, OH, with two hydrogens where you attacked it. Okay, same thing happens with the borane. Right, so this is a source of H minus, right? So you're going to get attacked there, up, down, kick away. Right, but again, you're going to have another one of these come in and interact up, and so you're going to end up with the an alcohol plus two hydrogens. Okay. Now, same thing happens, right, so there we go, no problem. Oop. Okay, so, now for the preparations of acid chlorides, okay, we're going to go back a little bit, right, so with that, so again, remember we talked about if you needed to add, change an OH into a Cl, you would see SOCl2, thionyl chloride, right? So that there. If you want to take that same compound and convert it into acid bromide, you'd end up adding PBr3. Okay, this converts an OH into a Br. Okay, just like this one converts an OH into a Cl. Okay, so there we go. Okay, and again, depending on what you add, you're going to be able to do this, right? So if you're adding water, right, you're going to attack, kick down, kick away the chlorine, and as the chlorine leaves, it's going to grab a hydrogen, so you're going to end up with the carboxylic acid. anhydride, right? Again, the carboxylate is going to be your nucleophile. That's going to attack there. Up, down, kick away the chlorine to make the anhydride. Esterification, right? You just take the alcohol, the thing with the lone pairs, that's going to attack. Up, down, kick away. How about that? So you leave the alcohol. Now you can get some selectivity, right? So if you have this, okay, so if you have this versus this, okay, so notice how this one's a primary alcohol because this one only has one carbon attached to it, but this carbon here has two carbons attached to it, okay. Okay, so here we go. So that's going to attack there, up, down, kick away. This is going to be more reactive than this one, so you're going to get some selectivity for this. I know it looks kind of bad, but so that's going to react here, okay, to make the ester. Okay. Again, for the hydrogens, right? They're going to attack twice. Okay. Now, with this one here, same thing happens with the carbons. Okay. In this case, so let's say you had methyl grignard, and really it could be any carbon group at all, right? So again, this is a source of H minus, right? So here, and this would actually end up this would have to be an excess, so that's going to kick up, down like that. So you'd end up with the ester intermediate, CH3. Right, that again is going to be reactive to it, and so you're going to get another one coming in, up, down. Oh, excuse me, ester is going to be a ketone. Sorry, been doing this too long. Up, down. You're just going to get this up, right? So you're going to end up with OH plus two of these carbon groups attached. Okay, just like two of the hydrogens attached to it. You're going to have two of these methyl, in this case, methyl groups attached. Okay, but it works the exact same way, right? You get this reactive intermediate, and so it comes in here. And so whenever you're adding hydrogens or carbon groups, you're going to add two of them. So otherwise, you just add the one. Okay, organic copper, don't worry about it. Stuff like that. So preparation of anhydrides, right? So you go in. The easiest way to do it is to do acid chlorides, right? So you're going to get attack, up, down, kick away, some sort of carboxylate, and so you end up with the anhydride. Not too bad. But again, the reactions are exactly the same way. Okay. If you want to add an alcohol, right? So this phenol, right? So it attacks here. Again, I'm going to give you a symmetrical anhydride, so it's attack one side, up, down, kick away, one of the groups, and you end up here. So this is aspirin. Okay. If again, an amide, right, is going to be more nucleophilic than a hydrogen, or not hydrogen, an OH group, right? So you get the nitrogen selectively coming in, attacking, up, down, kick away, to make, in this case, acetaminophen. Okay. Okay. For properties of esters, right? So these are all really good. So esters are typically very nice smelling compounds, right? So a lot of the essential oils, right? So that flavor for pears, bananas, orange, pineapples, and apricots, those are all esters, part of it, just depending on how long the different sides are, something like that. So not that you know those, but interesting. To making soaps, okay, so but that's for making for making lye soap, right? So all this is you take lye, which is a form of sodium, can make sodium hydroxide. The OH comes in, attacks here, kick up, kick down, kick away of your ester group, of your triglyceride. Okay, kick this away. So now you've got a long fatty tail, and then a charged bit here, and so it'll self-assemble so that all the oily bits are in the middle, associating with themselves, and then all of the carboxylates are on the outside near the water. Okay, so like that. So what ends up happening with the soap is if you have something that's salty, right, it's just going to be dissolved in the water. But if you have an oily stain, what's going to happen is it's going to see the sort of oily core of your soap and then hop in, and then it gets flushed away. So like that gets flushed away from the fabric. So that's how all the soaps do. It's just different soaps just have different head groups at the end. If they're charged, if they're positively charged, negatively charged, sort of just polar, just non-charged. So but they all end up working the same way. Okay, so cyclic esters, so they're called lactones, right? So they end up having the ester as part of a ring, something like that. So amides, right? So they're be very simple, right? So you have some sort of nitrogen group here, come in, attack, up, down, kick away, right? So end up with the amide. Again, hydride is going to end up going twice because you're adding hydrogens to it, right? So it's going to go here, up, down, kick away to form the aldehyde, and so on and so off. Right, so these things are going to end up reacting twice. Okay, again with Grignards, with carbon groups, again they're going to be adding twice. So whenever you add hydrogen groups or adding carbon groups, they add twice. Okay. Now for amides, right? So these things are incredibly stable, and so the chemistry ends up being a little different. Okay, so with that, so a couple of the reactions become different. The lactams, right? So these are cyclic. So lactones are cyclic esters. Cyclic amides are the lactams. So with that, right. So amide bonds are incredibly important in biology because that's what peptide bonds are. That's what's holding your amino acids together to make proteins. They're just simple amide bonds. Okay, so the preparation is pretty much from anything, right? Because they're at the bottom of that list, and so anything above it, you just add a nitrogen to it, and it'll go down. Now, if you want to hydrolyze it, it's incredibly difficult to do, right? So you can take water as a nucleophile, and you can boil it in concentrated acid or base, and it may or may not break, stuff like that. So it's incredibly difficult, incredibly energetic, because amides are such a difficult bond to break. That's why you can cook your corned beef for 6 hours. You can boil it for 6 hours, and it's still, the proteins are still there. They've just been denatured. The secondary structure is gone, but the protein itself is still stable. Okay. You can also use an enzyme. This is actually a preferred way of doing it. Proteases break down proteins. They do that by breaking this amide bond, and so they have aligned charges and stabilization such that you can actually break the bond. So those worked out pretty well. Now with the lithium aluminum hydride, one of the things that actually ends up happening is if you have an amide. Okay, this only works with an amide. If you hit this with lithium aluminum hydride, okay, typically you have a hydrogen up, up, down, kick away, and then you have two. That's not actually what happens with amides. What ends up happening is you actually end up taking out the C-double-bond-O, and so what you would end up with is that you end up with the amine. It's one of those really quirky things. Okay, so but you go amide to amine by adding lithium aluminum hydride. Go figure. Stuff like that. So that's one of the weird things. You do see thioesters and phosphates in biology. So acetyl-CoA, which is important for making lipids and stuff like that. So this is just a thioester, right? So here's the acetyl-CoA part here is just a giant leaving group. Okay, that's all it is. And all you're really interested in is that 2-carbon piece there. Okay, but there's a thioester that's where it breaks. Okay, so this can come in, right? So if you have an amine, so you have glucosamine, you have the amine come in, come in here, up, down, kick away, the CoA, that's just that leaving group, and you end up with an amide. You go from a thioester to an amide, you're dropping in that list, and you're good. So this is how you make N-acetylglucosamine. Okay, so polymers and polyamides, right? So these are incredibly important for polymers, right? So you can either take, you have a diamide or a diol. Okay, so with that, depending on which kind you make, you add it with an acid chloride, with either acid chlorides on either side or acids on either side, and you react it together, and so you get these sort of blocks of A, B, A, B, A, B, A, B type polymers. Okay, so either if they're connected with amide bonds, they would be polyamides. If they're with ester bonds, they'd be considered polyesters. Okay, so some of these are pretty, these might be kind of hard for you to see, but depending on like the lengths of the chains, right? So nylon 6,6, which means it has 6 carbons in the nitrogen piece, and six carbons in the nitrogen piece, 6 carbons in the diacid part, right? That makes nylon 6,6. So this is in fibers and clothing. So with that, so you can make this ester here with dimethyl terephthalate with ethylene glycol. You make mylar, caprolactam, and so this is actually just nylon 6. So because it has both the acid and amide and amine parts within it, so with that, it's actually you only need one piece stuff like that. So if you make polycarbonate, right? So this is very similar to these are polyesters, right? So with that, but you have a carbonate group instead of a carboxylic acid, stuff like that. And then you can also have this group here. This is polyurethanes. These urethanes end up making polyesters, stuff like that. So right, so the way that you usually do this is you have a adipic acid, stuff like that. So this is 6 carbons long and hexamethyldiamine. So you have 6 carbons long with amines on either side. You heat this up to incredibly high temperatures, 280 degrees Celsius. So the water boils away, and you end up with an amide at the end, and so you get nylon 6,6. Stuff like that. So polyesters are incredibly important for tire, for things like tires and mylar balloons, and some fabulous. I don't know if you can see, hopefully you can see just these fabulous polyester suits, stuff like that. So plaid double knit casual suits. According to the catalog, the jacket was $16. The pants are $14. So you get a whole bunch of them, mix and match. It's wonderful. But the way that they do this is the polyester, and this is Dacron or Mylar. You make sort of ethylene glycol. This comes in, it attacks, up, down, kicks away, and so you end up with a nice polyester, stuff like that. So polyamines, polyesters, right? So if you need things, so these are difficult. The biology doesn't know how to deal with these, right? So biological systems, so they don't get broken down. That's why they last for 1,000 years in the landfill. But for things that biology knows how to deal with, stuff like that. So glycolic acid, lactic acid, 3-hydroxybutyric acid. If you make polyesters out of those, biology can understand those, right? So biological systems can do that, right? So if you have sutures that dissolve, right, because you have enzymes in your body that know how to break those things down, right? Biodegradable polymers. There's bacteria in the landfill that know how to break these down for food and stuff like that. And so if you have so there's an increasing push for these biologically. Not only are these sourced biologically, you make these through fermentation, so you don't have to use petroleum products for the carbon. But the biology, you go and put these together through heat. It's a very simple reaction, and then once they're put in the landfill, they can be recycled. Sort of processed into the food web. Stuff like that. So IR spectroscopy, IR NMR, just take a look at that stuff. There's some homework problems. You won't have the test. They won't be on the test. It'll be on the final. So don't forget to practice those. One thing you want to know, right? So we talked about lactams, right? So one of the more important classes of antibiotics is these beta-lactams, right? So these are the first really important antibacterials. So the penicillins and cephalosporins, they both have this cyclic this lactam here. So it's a 4-membered ring lactam. This makes these incredibly energetic, right, and unstable. And the fact that they're unstable means that they're reactive and stuff like that. And so what ends up happening is these compounds, so penicillin, actually shuts down cell wall biosynthesis, so by that, so it reacts with an enzyme called transpeptidase, so by that, and stops cell wall biosynthesis, and so that's so it doesn't actually kill the bacteria; it just keeps it from dividing, and so it sort of keeps the bacteria at bay until your body can get up and running with and mount its own immune response to kill the bacteria. And so that's why you have to take it for 10 days, because you don't know how you have to keep it from dividing until your body can clear it out, stuff like that. But it doesn't actually kill it, stuff like that. And so what happens, why we get resistance, is that there's been enzymes that the enzyme transpeptidase is mutated so that this penicillin can't get in there to bind it up, stuff like that. And so what you do is this side of the penicillin, you put different groups on here to be able to overcome the resistance of the transpeptidase and keep being able to inactivate it. So amoxicillin, penicillin, ampicillin, things like that. The only difference is they have different groups out, slightly different groups out here. So with that, but they all work the same way. So good luck.